Hello everyone. Today I will solve questions from chapter 6 and I will solve a few questions from the beginning of chapter 7. Chapter 6 is about frequency response and chapter 7 is about Z-transform. These two concepts are closely related to each other. Before I begin, I want to remind you an important relation. We have already seen the difference equation. In the difference equation, we represent the signals in the time domain. Frequency response and Z-transform are representations of these signals in different domains. And there is an important relation between those three. The coefficients of okay, let's consider this difference equation between the input and output. The same coefficients, we have the same coefficients between the input and output for frequency domain and Z-transform. You will understand what I mean in the example questions. Okay, let's start with the first question. In this question, we are given this difference equation. In part A, we will find the frequency response. Sorry. Okay. So frequency response of this system has the same coefficients with the difference equation. These are our filter coefficients. Coefficients are the same and the delay terms becomes the exponent terms in the frequency response. Therefore, frequency response of this system will be this result. We can simplify it further so that we can obtain the magnitude and phase values. There's a common trick to obtain this phase and magnitude values. You check the exponent terms. In this case, the exponent terms are 0, minus j omega, and minus 2j omega. You find the middle one, which is minus j omega. You take it out of parentheses here. So inside parentheses, we are left with this. Using Euler's formula, we can see that this summation is equal to cosine term. Here, magnitude of this term is 1. Therefore, it will represent the phase shift. And this will represent the magnitude of the frequency response. In part B, we will find the period of this frequency response. While finding the frequency or periodicity, we can ignore the DC term. What is the frequency of this signal? It is 1 over 2 pi, and this is 1 over pi. So the fundamental frequency is 1 over 2 pi. Therefore, the fundamental period is 1 over f, which is 2 pi. You can see the plot of these signals using the MATLAB commands. Here you will see that at some values of omega, the frequency response is 0. And this part is about that. It is asking to find all frequencies which the output response is 0. So in time domain, we used to have convolution operation, and we were using it to find the output of a signal. In frequency domain, we don't need to do that complicated operation. Instead, we can directly multiply the frequency response with the input at the corresponding frequencies. So when we do that, at these frequencies, the output will be 0 since the frequency response is 0. Um, Let me clean the screen. Um, okay, here is part D. We will find the omega values, which makes frequency response 0. So this is our frequency response. Magnitude of this term is always 1. It is never 0. So we will find the omega values, which makes this expression 0. And then when we solve it, we will see that these omega values makes the frequency response 0. Therefore, the output becomes 0. In part E, let me clean it. Okay. In part E, we are given this input signal and we will find the output signal. The input signal is at a particular frequency, which is pi over 13. So in order to find the output, we should find the frequency response at this frequency. Um, we need to find h omega at pi over 13, and it is equal to this value. And we will simply multiply it with the given signal. We always use the cosine, so we convert this sine signal to cosine. There will be pi over 2 phase shift. So we directly multiply them. This will be the magnitude. This will be the phase shift. Therefore, this will be our output. In this question, we are given this difference equation. First, we find the frequency response. So we simply use the same coefficients, 1, 2, and 1. Delay terms becomes the exponent terms. Therefore, we can write the frequency response like this. I will skip this plotting part. In part C, determine the output when the input. So the difference of this question from the previous one is that this time the input has two different frequency components. The first component of this signal has frequency of 0, this DC term, and the second component, it has frequency of pi over 2. So we need two values of frequency response, which are h0 and h pi over 2. We will multiply this DC term with h0, and we will multiply this cosine term. This cosine term can be written in this form by using Euler's formula. So we will multiply it with the h pi over 2. Actually, we will multiply the first part with h pi over 2 because the frequency is pi over 2 here. And here the frequency is minus pi over 2. So we will multiply that part with h minus pi over 2. So this will be the final result. If the input is delta n, then we can directly use this difference equation and replace xn with delta n. So this will be the output. Why don't we use frequency response here? Because delta n is an exceptional signal. We cannot talk about its frequency. Therefore, we use the difference equation in order to find the output of this signal. So based on the question, we will choose different strategies. For some, while calculating some outputs, difference equation is more practical. For some other inputs and outputs, frequency response is more practical. So we will choose the method which is more appropriate for us. In part E, this time the input signal is a unit step sequence. Again, for this input type, we will use difference equation. When we use difference equation, this will be our output. Here we see that when n is less than 0, output is 0. When n is between 2 and 1, output is 1. I mean when n is equal to 0, actually. When n is equal to, when n is equal to 1, then the output will be equal to 3. Because these two terms will be now 0. When n is equal to 2 and greater, output will be 4. In the next question, again, we are given this difference equation. We find the frequency response using this filter coefficients. In this step, we use the manipulation technique I have explained. We take e to the minus j omega out of the parentheses, and using the terms inside the parentheses, we use Euler's formula, and it becomes 2j sine omega. Here j is equal to e to j pi over 2. Again, I will skip this floating part. Determine the output if the input is. Here we need h0 for this DC term and h pi over 4 for this cosine term. H0 is equal to 0. When you put a 0 here, sine 0 is 0. Therefore, h0 is 0. H pi over 4, h pi over 4. When we put pi over 4 in this expression, we get this value. Here we see that the magnitude changes square root of 2 and phase changes pi over 4. So we multiply the magnitude of this cosine term in the input by square root of 2. Here, this cosine term, where in part C. We multiply the magnitude by square root of 2, and we apply phase shift of pi over 4 here. Therefore, this minus pi over 4 will be cancelled, and the final result will be square root of 2 cosine pi over 4n. Let's move on to part D. This time, the input signal in part C is multiplied by this unit step signal. And the question is asking for which values of n corresponding output will be equal to the output obtained in part C. So here, when we put this input in the difference equation, we get this relation. When n is greater than 2, this equation is the same with the equation in part C. Therefore, we can say that for the values of n which is greater than 2, corresponding output will be equal to the output obtained in part C. Um, In this question, we are given the frequency responses and we will find the impulse responses. So we will go back from frequency domain to time domain. We will use the simple fact that their coefficients will be the same and this exponent term will be delay term in the impulse response. So for example, for part A, coefficients are 1 and 2. So here our coefficients are 1 and 2, and exponent terms are 0 and minus 3. Therefore, corresponding delay terms will be 0 and minus 3. As a result, this will be our impulse response. For other parts, we can find the output with the same way. So I will skip the other parts. Okay. So far we have been given difference equations. This time we are given frequency response, and in part A we will write the difference equation. In order to do that, first we need to do these multiplications. When we do that, we get this result. Now it is in the form of summation of complex exponentials, and we can find the one-to-one correspondence between the coefficients of this frequency response and difference equation. Filter coefficients are 1, 2, 2, and 1. And delay terms are 0, minus 1, minus 2, and minus 3. Therefore, difference equation can be written like this. If the input is delta n, we simply replace this xn term with delta n, and we get this impulse response. Actually, I don't think that the result should be this value. So these are our filter coefficients, and we will multiply them by delta n minus 1, delta n minus 2, and delta n minus 3. Therefore, the result should be delta n plus 2 delta n minus 1 plus 2 delta n minus 2 plus delta n minus 3. But in the solution, it says that identify the impulse response values as the filter coefficients, which are also okay. This result is not correct. It should be, as I have explained, delta n plus 2 delta n minus 1 plus 2 delta n minus 2 plus delta n minus 3. In part C, if the input is in this form, for what values of omega, output will be 0. For that, we will find the omega values which makes this frequency response 0. There are three different values. The one that makes this term 0, this term, and this term. When we solve for each case, we find these omega values, which makes the frequency response 0. Therefore, the output will be automatically 0. Again, we are given frequency response, difference equation. For the difference equation, first we do the multiplication. This is the result of multiplication. And difference equation will be xn minus this value times xn minus 1, this value times xn minus 2, and 1 over 4 xn minus 3. I will skip this part. We have already done it several times. Again, this is exactly the same as in the previous question, so I will skip it. So let's move on to the next question. Here, this question is different from the previous ones. In the previous ones, we were given the input-output relationship in time domain by difference equation, or in frequency domain by frequency response. This time, we don't have such a closed formula, but we have three observations. In the first observation, if the input to this signal is delta n, the output will be this value. If the input is this cosine term, output is 0, and if the input is this cosine term, the output will be this value. By using these three observations, we will solve the following questions. I will skip this plotting part. Determine the output when the input is this value. So we know the impulse response, and this signal is a superposition of different impulses. Therefore, we can use superposition to find the output. The impulse response is delta n minus 3. So response for this input will be 3 times of the impulse response. Response of this component will be minus 2 times shifted version of the impulse response by 2. And this will be the impulse response shifted by 3. And the overall output will be their summation. So we took advantage that this system is linear time invariant. In part C, this time the input is a cosine signal. We need to find the impulse response when the frequency is pi over 3. So in this example, we have a signal with that frequency, and when we look at the output, we see that the input is multiplied by 2. Therefore, we observe that a here h pi over 3 is 2. We observe this from this input-output relation. Therefore, for the input in part C, output will be 2 times of this input. In the last part, we need to find the frequency response for pi over 2. For that, we will use our observation from this impulse response. We know that the filter coefficients are the same with impulse response and frequency response. Therefore, using these filter coefficients, we can find the frequency response. And when we insert pi over 2 for omega, we see that h pi over 2 is 1 plus j, which is not equal to 0. Therefore, this statement is not true. It is false. I think we have 5 questions left. Okay. In this question, again, this is different from the previous ones in a way that in the previous questions, we had only one system. In this question, we have 3 subsystems. And in part A, we will find the equivalent system that is a single operation from input to output by using the given difference equations. We will go step by step. First, x3 in this subsystem is equal to y2. Therefore, we will replace x3 with y2. This will be the result of that operation. Then we will replace x2 by y1. So in this step, we get the result of that operation and the final result, which shows the relation between the x1 and y3, or the input of the overall system and output of the overall system, is this equation. In part B, we use the frequency response to write one difference equation that defines the overall system. Okay, so this time we write frequency response of each subsystem. Then we know that if they were impulse responses in time domain, their convolution would be equal to impulse response of the overall system. However, we know the frequency responses. These are in frequency domain, and overall frequency response is equal to multiplication of the frequency responses of subsystems. When we do the multiplication, we get this result. So what's important here? It is that in time domain, we need to do this complicated convolution operation. However, in frequency domain, we can simply do multiplication. Here we are given the frequency response of a system, and we will find the output for this given particular input. In this input, we have three different frequency components: the DC term, pi over 2 frequency, and this delta signal. So we cannot, using the frequency response is not practical for this input. Therefore, we will use the difference equation in order to calculate the output of this part of the input. For the DC term, H0 is equal to 4. So we simply multiply DC term by 4. For this pi over 2 frequency, frequency response is 0. Therefore, that part of the signal will be multiplied by 0. For this term, we will use difference equation. In order to find the difference equation, first we do the multiplication and get the impulse response as the summation of complex exponentials. Then we get the filter coefficients. Using those filter coefficients, we find the impulse response. Therefore, we know the output of the system for this shifted and scaled impulse signal. Overall response of the system will be summation of each part. That was all for the frequency response. That was all for the chapter 6. I will solve 3 questions from chapter 7. In this question, we are given different impulse responses. No. We are given 4 different signals, and we will find their Z-transform. So as I have mentioned at the beginning of this recitation, Z-transform is just representation of a signal in a different domain. And the formula for finding the representation of a signal in Z domain is given here. Oops. Here. So if we have our signal sequence in N domain, the delay terms becomes the exponent terms of Z, and coefficient of the Z terms are coefficients of the Z minus Z to the power minus K terms are xk terms. Okay, by knowing that, now we can find the Z-transform representations of the given sequences. For x1, this is non-zero only when n is equal to 0. So all the powers of z will be 0 except z to the power 0, which is equal to 1. Z to the power 0 is 1. And its coefficient is x1, 0, which is equal to 1. Therefore, Z-transform representation of x1 is equal to 1. For x2, it is non-zero only when n is equal to 1. When n is equal to 1, we need to find the coefficients of z to the minus 1 will be non-zero, and it will be equal to x2 when n is equal to 1, which is equal to 1. Therefore, this is equal to z to the minus 1. x3 is very similar, just the late term is different. So z to the minus 7 will be non-zero, and its coefficient is 1. x4 is superposition of the x1, x2, and x3. Therefore, we can use this superposition to find the signal representation in Z domain. Am I correct? Let me check it. Actually here the delay terms, this delay term is different. So we can use superposition for this part, and for this part we need to apply time delay property. Time delay property tells that if the Z-transform of x1 is capital X1, then n0 xn minus n0 will be represented in Z domain as z to the minus n0 times x1. So the delay term becomes the exponent of this z multiplier. Therefore, this will be the overall result. In this question, we have two subsystems, and they have the same impulse responses. Both impulse responses are this. First, we find the system function. So, in n domain, we used to call Hn as frequency response. In frequency domain, we used to call it frequency response. And in Z domain, we call it system function. Okay. So impulse response, frequency response, and system function, they all have the same coefficients. Only difference is that the delay term in the impulse response becomes the exponent term in frequency domain and Z domain. Therefore, by using the same coefficient values, we can find the system function of the two subsystems. In part B, we will find the system function of the overall system. Remember that in n domain, we used to do convolution between impulse responses of subsystems. In frequency domain, we used to do multiplication. In Z domain, again, we do multiplication. So we simply multiply the system functions of two subsystems, and we get this result. Okay, this was the last question for this recitation. Thank you for listening. Have a nice day.